Hello, in this video we're going to look at how to select and filter data in the Data Analysis module of Mercury. First, we need some data to analyse. In this example, the data has been generated from a conquest search. The search itself was for metal-metal multiple bonded dimers where the metal is chromium, molybdenum or tungsten, with the following parameters defined: the metal-metal bond length, the atom label of each metal, and the number of connected atoms of each metal. You can find resources for creating 3D searches in Conquest in the video description. You can transfer 3D search results from Conquest to Mercury using the Analyze Hit List and Analyze Data features in Conquest. The Data Analysis module in Mercury also reads in C2M files which can be exported from previous sessions of Conquest. To export from Conquest, go to File and then Export Parameters and Data. Ensure the file type is set to Mercury Data File and that the Include Defined Parameters box is ticked. Then click Save and choose a suitable file name and location from the Explorer. This method is best if you want to examine the results in different sessions of Mercury. The next step, if choosing this method, is to open an instance of Mercury from the Start menu or from the desktop icon. Note that if you are transferring results immediately from Conquest, this will happen automatically. A C2M file can be opened from the File menu in Mercury by choosing Open and selecting the file from the dialog. When the file is opened or transferred directly from Conquest, a hit fragment display dialog and data analysis window, in addition to the main Mercury window, will appear. The hit fragment display option window can be used to change how the 3D measurement is displayed on the structure. In this case, the relevant bond is in a cap stick style and the measurement is labelled adjacent to it. We do not need it, so it can be closed. In the Data Analysis window, you will see that we have several columns, which includes, amongst other things, the ref code and fragment, which is relevant if there's more than one 3D hit per molecule or if there are multiple unique molecules with hits, and the parameters that were specified in the search with BD_len, lab and TCN indicating bond length, atom label and number of connected atoms respectively. We will use a histogram to illustrate why you might wish to filter data, so first we select the bond length data by clicking on the column header. Then, from the Plots menu, select the histogram option. As you can see, the data spans from 1.7 angstroms to just over 3 angstroms, with the largest cluster centered somewhere around 2.1 angstroms. Given that we have 3 different elements and a variety of coordination numbers, the current plot isn't very helpful for understanding the data. Let's see how it breaks down by element. First, make sure that the bond length column is deselected by clicking on the header. Then we click on the column lab1, which is the atomic label for the first of the 2 metal atoms in the dimer. If you scroll through the results, you will see that all the hits have the same element within the pair of metal atoms. Therefore, we can just use label 1 as a filter. From the Selection menu, choose Filter to open the Filter window. We will choose Starts With from the drop-down menu, and then type the element we are interested in and click Apply. We will look at chromium first. We can see that the relevant data are shaded grey in the spreadsheet, and in the histogram window, the bins have been shaded according to how many chromium dimers they contain, in red. Unsurprisingly, the shortest bonds are associated with chromium, but the range of bond lengths is quite large. If we repeat the process, but with the filter for molybdenum instead, we find then there do appear to be at least 2 regions where the bond lengths fall, most measurements occurring between 2 angstroms and 2.3 angstroms, with relatively few structures from 2.3 angstroms to 2.4 angstroms, after which we find another broad distribution of structures which diminishes up to the 3 angstrom region. Repeating the procedure for tungsten, the pattern is a bit less clear. It's possible to store a selection by going to Name Selection. First, we will apply the molybdenum filter again. We click on the Selection menu, then from the Name Selection option, we will call the selection molybdenum and add a description, molybdenum dimers with metal-metal multiple bonds, and then click Save. After doing so, from the Selection menu, the saved selection can be found in the Selection drop-down menu. Click on any line in the spreadsheet to clear the selection. From the Selections menu, go to Selection and choose molybdenum. After applying the selection, you will see the molybdenum dimers are once again highlighted in the histogram. Let's say that we wish to plot a histogram of only these molybdenum dimers. This can be done by going to the Selection menu and clicking Show Only Selected. If we now select the bond length column and go to Plots and Histogram, it will contain only the data relating to the molybdenum selection. We could do this for chromium and tungsten too, but we will instead apply another filter. Whilst it's possible to apply multiple filters to the whole dataset, applying a filter to a selection will make the interpretation easier. In this case, we shall select both of the columns with the number of connected atoms, TCN, and then go to Selection and Filter. You can now see that we have 2 filters, one for each column. As the data is numerical, the filter is a slider rather than text filter. As opposed to the metal elements, the coordination numbers do vary from one metal to the other in each dimer, so a little more experimentation is required. If we keep the number of connected atoms between 3 and 4, meaning there are from 2 to 3 donor atoms from the ligand set coordinated to the molybdenum, the distribution of the relatively small number of structures peaks around 2.2 angstroms. And if we pick a random selection from the spreadsheet, such as BEDZAN, we can see that they are classified as triple bonds. On the other hand, if we move the sliders to between 5 and 6, so 4 to 5 donor atoms from the ligand set, we can see that the vast majority of structures occur in this range with the modal bin around 2.1 angstroms. Inspecting a selection of structures from the modal bin by first clicking on it and then choosing an entry from the spreadsheet, such as BELWEU, we can see that it involves a quadruple bond. It's also interesting to examine those complexes with a greater number of connected atoms, as it's not immediately obvious what type of ligands they might relate to. If we select the number of connected atoms to be between 8 and the maximum in each slider, most of the selected structures span bond length from about 2.45 angstroms to 2.85, with a few structures at the tail ends. If we look at a few structures from the bin around 2.65 angstroms, for example BOWCEV, we can see that they typically have cyclopentadienyl or other pi coordinating ligands, which increases the number of connected atoms substantially. Often, the associated bond orders in this type of complex are lower, typically double bonds. To summarize, we have shown that gathering data from a general search, followed by the application of filters and selections in the Mercury Data Analysis module, can provide a convenient and efficient way to group and analyze large and complex datasets. If you would like to find out more about the functionality available in Mercury, check the links in the description and the playlist at the end of this video. We hope that you found this video helpful. Thank you for watching, and don't forget to subscribe to our YouTube channel.